This video is again about the control flow of a program. Compared to the previous videos about the control flow of a program, this is more focused on the technical background to get a better understanding about what happens on a computer when you execute your program, what needs to be done by a compiler to actually generate machine code so that the computer actually can execute your program. And here we want to keep things very simple because we have to focus on technical background. That means in all these examples, we only consider one function main. And that means in an example like here, we just have to consider this part, the body of function main. And the entry point in this case would be the first statement after the open curly parenthesis, this first printf, which prints A. Then the control flow goes in this direction, so we would print B, then C, and then when we reach the closed curly parenthesis, we reach the exit point of this program and we exit the program. So simple to understand. And also the meaning of sequential execution of a program obviously makes sense because we write down these statements in a sequential order, and that's why we expect this behavior, why we expect this control flow. Now, in a previous video, you saw how if statements or loops, like for example a while loop, can be used to change this control flow. That's why these are called control structures. What you see here in an example is also some language feature for controlling the control flow, the so-called gotos. And you will see in this example why some people say you should not use gotos, because it's hard to maintain software that is making at least too much use of gotos. But let's first understand what is going on here. We have here labels and statements with a goto. Here is a label B, here is a label A, here is a label C. Now you will later see that these labels are just something the compiler needs for doing some kind of bookkeeping. It will not generate code for labels, but it will make use of it when you, for example, use a goto statement. Like, for example, here, here, and here. And the meaning of this goto statements is that you simply continue the execution of the program after a certain label. And the label is given after the goto keyword. And that means when you run this program, the following happens. We still have here the entry point, and the control flow starts with the first statement, then with the next, and so on. But here, the goto influence what the next statement actually is. After this goto A here, we continue after label A with this printf. Then after printf, we continue with goto B. Goto B means that the execution continues with the first statement after label B. That means with this printf here. Then it continues with goto C. Goto C means the next statement that gets executed is the statement after label C. That's here. And then we actually reached the closed curly parenthesis of function main. That means we reached the exit point. That means here we exit the program. So that means it simply prints A, B, and C as before. But you see, when you visualize the control flow, it's harder to understand what happens when you run the program. What statement gets executed first, second, third, and so on. And you see why some people say you never should use gotos, because it's very hard to maintain programs with gotos. So why am I showing you this gotos? The reason here is, as I said in the beginning of the video, to give you a better understanding of what is technically going on in the execution of a program. And you will see gotos are something that you basically have also in a similar way in assembly code. So when you write a program in C just by using gotos, or in ABC with just using gotos, it's easier to see how the compiler generates assembly code from it. Before I actually go low level, you see I made another modification. I simplified the program. For example, I now just have one goto which makes it easier to visualize the control flow. And I'm using putchar instead of printf. The reason for that is when we start programming in assembly on our own computer, there actually will be a machine instruction for our computer for printing a single character. And that means one of your first assembly programs basically can implement this part here. So when I now give you some idea what is technically going on, you just have to be a bit patient, because in a few lectures you basically will do what I describe here by yourself. And that means you will write a program where the execution starts here with the putchar, which will be a actually machine instruction. So this will be the first instruction that gets executed. Then you will see that this label B is really not an instruction, it's just a bookkeeping, which when you do assembly programming needs to be done by yourself. Here it's done by the compiler. It's needed to mark or remember that label B refers to this instruction, to the putchar printing a B. So back to the control flow, we first print A, then we print a B, so the control flow goes in this direction. But then it actually just goes to the goto B, which will be a jump instruction in assembly. And this jump instruction means that the next instruction is again this putchar instruction. And that means we have here some loop, an infinite loop, which is just printing B, C, D, E, F, and then again B, C, and so on. And that means, for example, this instruction never is reached. And it also means that our program never terminates. So far in this top-down approach, we just consider the computer to be a black box. Now, to get an understanding of this technical background, we of course have to look into this black box at least a bit. And with this picture, I basically describe on a higher level the computer that we will build, its components. And here I first want to focus on the component called here RAM, the random access memory. What it means that you have here a bunch of memory cells organized in an array with addresses. And then I also will mention a bit more about the CPU. So on this slide, we focus on these memory cells. You see here a bunch of memory cells. This is a visualization of a memory cell, this, and so on. And actually, in a computer, we have lots of memory cells. So this goes on here. Let's visualize it like that. Let's assume, to be concrete, that we in total have 1024 memory cells. That would be 2 exponent 10, and that would be 1 kilobyte. Now in each memory cell, you can store a certain amount of bits. The measure, the kind of physical unit for the size of a memory cell is called a byte. And usually a byte is, at least nowadays, 8 bits. There used to be computers where a byte was 9 bits, but nowadays I think we actually could skip this and could say, okay, the size of a byte is 8 bits. And that means in a memory cell you can store 8 bits and you can represent this with 2 hex digits, which is kind of nice. Now, something really important is that each of these memory cells has an index or a label, a name you can refer to a certain memory cell. Now, the right term for it is actually the address of a memory cell. And the first memory cell has the address 0. So we start counting with 0. And that means the second memory cell would have the address 1, and so on. And this is the reason why I wanted to be concrete about the number of memory cells. That means the last memory cell would have the address, in this case, 1023. Now, after this quick look into the random access memory, let's have a closer look into the CPU. The CPU also has some memory cells. These are actually called registers, but technically they're also just memory cells. And on our computer, we will denote these memory cells, these registers, with %0, %1, %2. So you also can store some data in this memory cell, for example, in these registers that you see here. And on our computer, the size of these registers will be 64-bit. Now, what you can do with instructions on our computer can be categorized. Some of these instructions will actually do some computations, for example, adding numbers. But these computations only can be done with values that are stored in these registers. And we will call this ALU operations or ALU instructions. ALU is short for arithmetical logical unit. That means if you somehow store, for example, here the value 1 and here the value 2, then you, for example, can perform ALU instruction, which is adding register 0 with register 1 and stores the result in register 2. That means after this instruction, you would have here a 3. And of course, there are other instructions, for example, subtraction, multiplication, division, and so on. And you will see in this bottom-up part of this class, we will actually build this in one of the next lectures. So this is one kind of instruction that you can perform on our computer. Another kind of instruction is moving or copying data from the random access memory into CPU registers. These kind of instructions we will call fetch instructions. And there are different kinds of instructions, as you will see. But for short, just let's pick out one kind, which is, for example, copying here this hex 61, let's say, into register 0. That means after this operation, you would have here the value 61. And of course, a few details need to be resolved because somehow you have to describe how to fill up the remaining bits. But let's focus on the essentials. You somehow can move data from the memory into a CPU register. And another kind of instruction is basically doing the opposite. It's copying data from a register into memory. So for example, with a so-called store instruction, we would be able to copy this hex 61 into a memory cell here, let's say into this memory cell. So with that, we have a rough idea what at least our computer that we will build basically can do. But you will see that the computers that you actually can buy and that you're using are really very similar to that. A few things are maybe more advanced, but essentially we have seen here three kinds of operations. It can do operations on data that is stored in CPU registers. It can copy data from memory into CPU registers, or it can copy data from CPU registers into memory. And for our computer at least, we also can consider I/O instructions as special fetch or store instruction. If you read something from an input device into a CPU register, then it's basically a special kind of fetch instruction. It's just not moving data or copying data from the memory into a register, but from the input device. So let's say a user types in an uppercase A, that's in hex for 1, then you can fetch it into, for example, register 0. Or if you have hex for 2 in a CPU register, for example, register 1, then you could store it to the output device, or copy it to the output device, and then it would print a uppercase B. So what is actually missing here is another kind of operation, the so-called jump instructions. For understanding this jump instructions, we should have some rough idea how a program sequentially gets executed. And what I show you here will be one of the first examples that we run on our computer. Program consists of at least a few instructions, at least one instruction, and each of these instructions is represented by some bytes. On our computer, every instruction will consist of exactly 4 bytes. And in order to run a program, these instructions need to be loaded into memory. And the first instruction of a program will be loaded to address 0. That means at address 0, the next 4 bytes belong to the first instruction. At address 4, we therefore have the second instruction, or the second instruction starts at address 4, and so on. So this would be address 8, and so on. Then we have to build in our CPU some component called a control unit, which is responsible for actually running the program, for executing the instructions in a certain order. And the rules for that, what the control unit will realize, will be that the execution begins with the first instruction. And first instruction means on our computer the instruction at address 0. So that means the first instruction that gets executed is this one here. And this could be, for example, a store operation, a fetch operation, an ALU operation, or some IO instructions. Then, after the first instruction was executed, the next instruction should be executed. And the next instruction usually means the next instruction in memory. That means if the first instruction was at address 0, the second instruction is the instruction at address 4. That means we execute this instruction. And so on. And usually this is the control flow. One instruction after the other gets executed. Now this instruction here is special. This is a jump instruction. And the purpose of a jump instruction is to change this default behavior, what the next instruction actually is. So this instruction somehow specifies that the control flow should continue here. And that means after that we jump back to the second instruction, and the control flow would be something like that. So that means this last instruction here never would be executed. Now let me clean that up. So now once again the control flow, now I think it's better to see, would be that. So in this direction we first execute the instructions, and then with this jump instruction we jump back and continue with the second instruction. Now this is actually an example from before, and an example that you exactly like that will be able to program on our computer in assembly. Just assume that this instruction is basically the put jar for character A. And on our computer there actually will be instructions for printing a specific character. The character will be encoded in the instruction. And this instruction therefore could be the instruction for printing B, this for C, D, E, F. This would print G, but it's never reached. And this is the jump instruction for jumping back to the instruction that was marked with label B. Now, jump instructions actually come in different flavors, and what you have to distinguish are actually so-called unconditional jumps and conditional jumps. And the meaning and what you need them for, I want to explain with this example, where we go back to some program which is not using gotos, which is using a while loop. But you will see in the exercises, we will do things that you usually should not do. We will rewrite programs that have control structures like while loops, for loops, stuff like that. Actually, we will also introduce a so-called do-while loop and if statements, of course. And you have to rewrite this code in a way that it's closer to assembly, in a way where you actually use gotos for educational purposes, to better understand what the compiler is basically doing for you. Okay, now let's consider this example and let's write down the flowchart for the control flow. I skip a few things. We have variables n and res for result initialized somehow. We print out n and we print out result in the end. But essentially, I want to focus on this part. And for this, I want to draw the control flow. And then I will show you how to rewrite this with gotos in a similar way. And by that, you will also see this conditional and unconditional jumps. So the flowchart starts with this diamond shape with a condition in it. And the condition is n greater equal to. And depending on whether this condition is true or false, the control flow either goes continues here, in this case if it's true, and otherwise if it's false, we continue after the loop. And there we would have this print statement. Now, if the condition is true, we continue with result times equal n, and then we decrement n, and then we actually jump back. And I visualized it like that, or like that. But technically, this jumping back is a special instruction, as you saw before, a jump instruction. And if you want to represent this in assembly, then it's good to make here another diamond without a condition in it. So this is the difference here. Here we have a condition in this diamond shape, and here we do not. And this somehow illustrates that we need something which is going back to this condition here. Basically, you will see in C, this will be a goto. This will be also a goto, but in connection with a very simple kind of if statement. A conditional goto, you could say. Now, let's realize this with more primitive things like, as I said, gotos. And that's what you see here. So basically, here you see something that I called before a conditional goto. An if statement with a very simple condition, a condition without a logical or, logical and, just something where you check whether a value has a certain property, for example, and just one statement in this curly parenthesis. And this here is a unconditional goto. It always goes to its label. And now let's look at the flowchart of that. Again, I skip a few things. I skip this part here. I skip this part here, and I just focus on that part. And then you will see this is a primitive way to represent a while loop. Okay, so basically we have here a condition which either continues the control flow after label done or with this statement. So to visualize that, we would have a diamond n smaller 2. Then if this condition is true, then we actually jump to the label done or after continue after label done. So that means here I actually have to write true. Then I jump to this printf here. And otherwise, if it's false, we continue with the statement, which is res times equal n. After that, we decrement n. After that, we have our goto, which I represent in our flowchart just with a diamond shape without any condition in it. And the label basically means that I jump back to before this statement here. So you see the flowchart is kind of similar. A few minor things are different. Here the condition changed. Before it was a greater equal, but before we also had here false. And here we had true. But it's equivalent. Now, in exercises, you will do lots of things like that, where you have given some code with this nice loops, and you have to change the code into ugly code with gotos. And the purpose is not to train good programming practice. It's basically training you to later write assembly code, because with this kind of code, you basically have something which is very similar to assembly. And of course, it's also not the purpose of this class to train you to program in assembly for the rest of your life. It's just about understanding what the compiler is actually doing for you. And for that, we practice these skills of writing programs in assembly for simple examples. And that means that later you have a better understanding of what the tool that you are using is doing for you.